Thanks for the introduction and good morning, everybody. So I have the pleasure to give this last talk, and I think it's interesting to consider that historically the application and invention of statistical tools has very often been driven by the changing types of data and domain questions that we have in a particular scientific field. And it feels like with the many new data sets that we have in neuroscience, this may actually be what is changing right now in our space. I hope this is going to work. Right. So an interesting consideration is just to map the various things that we use in data analysis on an everyday basis on a timeline. And it turns out that the majority of the statistical tools that we use in neuroimaging are actually almost 100 years old. So most of them were used or were invented in the first part of the 20th century, which you can see in blue here. So those are things like Pearson correlation and all these special cases of linear regressions, such as ANOVA, t-test, and so on. And many other tools that mostly came up in the second part of the 20th century, such as bootstrapping analysis, random forests, elastic net, lasso that Alex talked about, and many others, they are only starting to be used in our domain. So there is a number of characteristics that seem to be changing from blue to red here. So one of them is the computational load. So many of the newer techniques, especially deep learning that is becoming popular now, they're just much more computationally intensive. And that already gives you a hint of why we haven't been using them or been interested in these types of models many decades ago. Another one is also that we tend to use always more nonlinear models more recently, such as random forests with variants like extremely random forests and so on. And that incurs problems that have already been mentioned this morning of interpretability sometimes. So as we scale to always more complicated models that can really take advantage of always more data, it may also be always more challenging to really draw rigorous conclusions from these data. So, but this is really the exact question that we and our collaborators have been interested in. What are actually the rigorous modes of drawing conclusions from data? So one way in which you can distinguish statistical methodology in general is by distinguishing into model estimation, but that's not itself drawing rigorous conclusions from data necessarily. And then statistical inference, such as null hypothesis testing, p-values, and so on, that appears to be the dominant theme in brain imaging today. And I think it's interesting to consider that predictions such as cross-validation out of sample generalization may be a different modus in some sense of drawing rigorous conclusions, extrapolating things that I learned from a particular set of data to a new set of data. So this is what we try to quantify in this study. What you see on the x-axis is just a linear model in the most common way used to just generate p-values. And on the y-axis, you see another linear model, lasso in this case, that uses out-of-sample generalization, so not p-value significance testing, to quantify how likely are we going to see a same pattern from other observations drawn from the same distribution. So, and across 100,000 simulations, here you see simulation data with various scenarios of noise, covariance situations and so on, we observe that there's something like perhaps an asymmetry between the best p-value that we got for any of the input variables and the best out-of-sample accuracy ranging from 0 to 100%. And that is most of the simulations gave you some statistically significant p-values, so it's to the right of this red line, but the out-of-sample generalization that we obtained with this same set of data, also a linear model, it was ranging between almost 0 to sometimes almost 100%. And on the other hand side, so here it is pictured in a different way, it was in a way easy to obtain statistically significant p-values. However, if you ask which of these models that have a decent out-of-sample accuracy do actually also show a p-value, then it's most of the time. Okay, so it seems that out of sample generalization in these simulations may be a more demanding criterion in some way, because most of the generalizing models are also statistically significant, but the opposite doesn't seem to be the case in this paper that we have preprint published recently. All right, so more concretely, how can we try to get at standard questions or common questions in the neuroimaging domain from a different perspective? So the default mode network is a dominant theme in brain imaging that we discovered almost entirely by chance as a textbook example of a serendipity effect. Yeah, we did not look for the default mode network, we just found the default mode network. And there are more than 1,000 papers every year on this topic, and there's hardly any psychiatric disorders that has not been linked to this major brain network. And what we've been doing over the last years with Simon Eickhoff and colleagues in the Research Center Jülich is to publish a paper on each of the nodes of this major brain network, and we think there is reason to believe that if you look at the heterogeneity of the connectivity to the rest of the brain, that there may be sub-regions in each of the major nodes of the default mode network that may perhaps be currently underappreciated in many of the neuroimaging studies. So once we have this sub-region version of the default mode network atlas, what can you actually do? Is this working? Okay. So here's an example of what we can do in healthy subjects. And this is in the example of mind wandering, so an important stream of research in psychology because it describes the class of cognitive processes that are going on when we are, for example, looking out of the window on the plane, flying to Singapore, and you're not thinking of anything in particular, but you just reminisce scenes of the past or project into the future of who you might need. So these less controlled types of thought processes are what people describe under the name of mind wandering. So, and it is typically described as a monolithic process in psychology and neuroscience. And here we wanted to know, taking resting state data only in the default mode network based on our subregion atlas and an extensive phenotyping of mind-wandering experience for this literature, an unusually large sample of 200 people, can we find evidence for distinct default mode signatures related to different types of mind-wandering experience? So here we used a canonical correlation analysis that is an extension of principal component analysis, and it helped us to demonstrate that there may be 3 different signatures, so all only in the subregions of the default mode. Yeah? So the model did not have access to any other part of the brain. And we see that different patterns in the default mode are related to different aspects of negatively related to emotion or negatively related to the detail of how people have these imaginary thoughts. So now the question is, how do we know this is actually a real pattern and we may see it again in other data? So the way we choose to look at this validation or generalization or extrapolation questions in the following way. We visited subjects that we haven't looked at before, and we took these 3 default mode subregion candidate patterns to relate them to different behavioral phenotypes that we have also not considered before. And it comes out that these standard ways to assess cognitive performance, working memory tasks, and well-being, they are differently related to each of these candidate signatures extracted in previous data. And that gives us some confidence that whatever turn out to be related to different types of mind-wandering experience may actually really describe some distinct properties of the brain. But how about clinical populations? So this slide tries to go into the direction of these RDoc vision of how to investigate psychiatric disorders, and that is how can we supplement these categorical labels that psychiatrists use in clinical practice every day? How can we supplement those by underlying dimensions of variability across psychiatric disorders? So, and what I didn't know, but my clinical collaborators at the Department of Psychiatry explained to me, is that many children diagnosed with autism, they actually have traits of attention deficit disorder also. And the same is also true the other way around. So many children diagnosed as ADHD, they also exhibit some symptoms of autism. And so that begs the question, is there perhaps an underlying brain correlate that links the two? So here we looked at this question in two of the biggest data sets for these two diseases, the ABIDE data set for autism, ADHD 200 for the other one, and we only looked at people younger than 21 years and only males, so this comes down to 1,300 people. And then we used something still untypical, Indian Buffet processes to come up with latent patterns of connectomic variability, but not using any of the labels. So these did not know about which person is ADHD or autism or healthy. And the unique property of IBP is that it can automatically tell you how many latent components are really in your data, which is why we chose this method. This was then fed into something more common, latent Dirichlet allocation. And it showed us that there may be at least 3 different factors of continuous variation across these 3 groups where we never used the labels to get to this point. But if you map them back into these 3 candidate axes of variation across 3 diseases, you see that there may be a continuous transition between health, ADHD, and autism. How about schizophrenia? So we also tried to depart from the subregion atlas in this 5-site sample of schizophrenic people across Europe and the States. And we first applied sparse inverse covariance estimation with nodes that are typically used in default mode literature in not only resting stage, such as on the previous slide, but also standard VBM brain structure. And we find that there's only some connections in brain function connectivity and only some kind of region structural couplings that are statistically significant if you use a usual granularity at which the default mode is studied. However, if you use a subregion atlas that has these much more fine-grained compartments, what comes out is that we confirm that these connections are related to the subregion compartments, but there's a much richer set of statistically significant differences in both brain structure and brain function in this schizophrenia sample with the subregion resolution. If we map this back to the brain, we make the following observation. We are less surprised that there are statistically significant differences within the default mode itself in schizophrenia. So this has been shown a large number of times. And what is interesting here is that we find that the default mode network and the dorsal attention network, so connections between these two networks, they were much more specifically disturbed. And the opposite is what we find in brain structure. So, of course, there are many disturbed connections within the default mode network, so this is not surprising, but it's not the default mode network on the dorsal attention network, but instead the default mode and the saliency network that have many more disturbed connections in brain structure. So, and kind of the tweak here is we used sparse inverse covariance estimation because it's sufficiently abstract to apply a same statistical model in brain structure and brain function. So the method is the same in both modalities. This allows us to really bring these two modalities to the same table in schizophrenia. All right. And my last example is this one here, in the space of schizophrenia again. And it's interesting to consider that over the last decades, there really have been a number of trends of how people chose to investigate schizophrenia. So here we have a semi-quantitative bibliographic chart, and you see that in the 50s, when PubMed started to log papers, we had still a lot of papers on psychoanalysis, which decayed over the time. In the 60s, people started to be really interested in dopamine, and it was only recently that we started to think about, well, perhaps schizophrenia is a social disorder. So this begs the question, can we perhaps have a quantitative way to know which parts of, for example, the mind may be most research-worthy in schizophrenia? So can we perhaps estimate from data which types of experiments we may want to run in the future. So this rather ambitious question is what we try to get at. And if you want to do this in the example of cognition, you just need to start from a description system of mental operations. So this is an unsolved problem, of course, but we chose the brain map taxonomy because it has been coherently applied to almost a quarter of the neuroimaging literature. So, and each cognitive class is linked to a robust map of convergence across the brain. And we consider this as accumulated quantitative neuroscientific knowledge from the neuroimaging domain, and came up with a pipeline that uses 9 different ways to use the maps linked to cognitive concepts to come up with neurobiologically informed features that are lower dimensional than the original space, and then have a stacking model approach. And what this allows you to do is to come up with if this is going to change here. Yeah, so it allows you to come up with this, and that is in one taxonomy of mental operations that has been applied to hundreds and thousands of studies in neuroimaging. You can say which ones of those are most helpful to tell apart healthy people and schizophrenic people in this multi-site data set. So, and this is my last data, and what we conclude from this slide is there is a number of things that have classically really been also the center of investigation in schizophrenia, and we confirm that these come up in this data-driven fashion to find kind of relevant cognitive domains, such as social cognition, but there's also several cognitive domains that we have not perhaps typically been focused on in schizophrenia research, and that may be interesting to look at in the future. And I think this is an exciting way to mine hypotheses from data rather than do data mining. Well, I'm going to skip this one and conclude that I think it's interesting to consider that statistics has been driven by domain questions and changing properties of scientific domains, and I think this is what is happening right now. I think it is interesting to keep in mind that classical null hypothesis testing has not originally been intended for analyses with thousands of people or tens of thousands of variables. And that may be why brain imaging is increasingly populated by high-dimensional statistics, what some people call machine learning, statistical learning, data science, and so on. But I think the real challenge is perhaps not even the engineering, but it can require differently nuanced scientific conclusions. But nevertheless, I'm optimistic because I think statistical pluralism extends the space of questions that we can ask about the brain and the rigorous conclusions that we can draw about the brain. Thanks.
Thank you, Danilo. Maybe I can ask